Welcome everyone. This is a lecture in quotation mark because please don't quote me on anything because I self-taught everything. But this is a really good intro to the whole subject, including how to practically set up a CFD. Um, we probably need 2 days because when I do the slides, I can't realize there's so much content I want to cover in depth. So we cover do like 1 or 2 hours today. Um, and then we just find another day for another lecture. Okay. So before we do the whole thing, CFD is really, really hard. If you put garbage in, you get garbage out, even worse. But you do get like colorful pictures. Um, Again, please don't quote me on any CFD knowledge if you're writing thesis or whatever. A lot of things is self-taught. So I would suggest you to do your own research when you're doing your own CFD setup. That is the best way to learn CFD. There's a really distinct difference between coding CFD and using CFD. If you're taking a fourth year course, that course will probably teach you how to code CFD, but we are learning how to use CFD today. Um, in the future, if you have a deeper understanding in this kind of field, make sure to update any inaccurate information I give here, because I appreciate after a year, more CFD knowledge, I would say like, oh, this is wrong. So make sure you do your own research. We'll focus on like the ANSYS software in terms of like some things, but we're not focusing how to use ANSYS. We're just focusing on the CFD technology. We'll go through most of the key concept, but we focus more on external flows because that's something that I have more experience with, and probably Rocketry needs more external flow. Got problem. 1 to 2 hours length today, I think. But note down any questions that you have and then ask the end of each section. It will be pretty structured presentation. Last thing, please go crazy on a CFD project to really understand what the technology is, the theory, and how to choose proper settings. We'll also cover a case study in this lecture. Look at Andrew 1, the most recent rocket that we just launched. It's pretty interesting too because it's supersonic rocket. More problems would occur when you do a supersonic CFD. And we also look at a test case with the NASA missile. That is a really well-studied geometry that we just look at it because it's just so well-studied. It gives you wind tunnel data. So it's a really, really good reference. So how would you learn CFD? Like, how do I teach everything myself? Of course, back to the basics, read a bunch of textbooks. This is probably the two best textbooks I can suggest. One is basic aerodynamics. You need really good understanding on how flow works in certain regimes. So it's a must to kind of like read about fluid mechanics and aerodynamics. Another textbook is basic CFD practical approach. This is the best CFD textbook I ever see. Most CFD textbook really focus on the theory, but not really how to use it or like give practical kind of guidelines. But this gives you like a really good guidelines, including different test cases. So recommended. I think they're on the team server already. So you can kind of dig through it. And then of course, online resource. Two YouTube channels are pretty good. Fluid Mechanics 101 is the best CFD channel I ever see. Really intuitive explanation. More theory heavy, but that's okay because you do need that theory side of knowledge. And our YouTube channel is Premier Aerodynamics. One thing that is really special is actually go through how CFD is set up, and it will also give comments on if that CFD is done well. So that's really rare on YouTube because it's a really well videos, and you have fun videos such as American Aerodynamics. There's way more fun videos to watch. yeah, this channel is really good. Um, Next one is a forum, CFD Online. It got basically everything. It's basically Reddit, Stack Overflow if you're coming from software background. It covers every single thing, including how to choose hardware if you're building a workstation, which is pretty rare because it's not something that you think that is important. Important note about online resources. When you see any YouTube tutorial with kind of the sign like, oh, x66 software, how to use, most of them teach you how to use the software, but not how to do a proper CFD. And we'll go over like some bad examples that I can find from those videos. Um, and CFD, again, if you don't understand the whole technology and do a CFD, you're basically just MS pinging it. It's basically drawing on a whiteboard is the same thing. If you're like with the Irish team, it would be like drawing Figma because you're just making colorful pictures and they're not meaningful. And some software specific kind of resource, user guide. Usually, user guide is like really complicated. The ANSYS software guide is like 4,000 pages. And then theory guide is like 2,000 pages. So just read what you need. Don't try to read everything. And of course, reach out your kind of like software provider because I think ANSYS even provides some consultation service. So that's something to keep in mind. So in terms of CFD, like what are we trying to do? Or like what is the back end of CFD? So the first thing that we need to look into is the way to solve a set of equations or differential equations. Um, Analytical analysis is basically you can write exactly a solution out, express it in exact terms. One of the best example in like mechanical side would be beam theory because you can exactly write out what the theory derived from a set of differential equations. So that's one of the best example of analytical analysis. Computational is a bit different. Computational, you're actually just guessing. The specific term is numerical analysis because sometimes the equations are so difficult that you cannot write or rearrange the whole equation. Um, One of the best examples is Navier-Stokes equation. If you think you can solve it, congratulations, you can win $1 million because it's actually a unsolved problem in the math um, sector. Um, yeah, so if you can solve it, congrats. Maybe give me commission too because I kind of like that this happens. Um, CFD again is guessing solutions. One of the I think the most kind of like everyone would know is Newton's method, like in calculus 1 or 2. Um, this means like again, if you use the wrong models, wrong assumptions, um, even just boundary condition will give you a really, really different solution. It's also a fight between error, inaccuracy, and computational time, and which we'll see more why this is the case. So computational methods is referring to how we kind of like break everything down into small control volumes and how we actually interpret the result cell by cell. So there's some this basically you're breaking down a domain into smaller control volumes, and there's different approach. It's actually pretty similar to FEA because we are basically doing the same thing here. So this is kind of the three most used method for CFD. It's finite volume method, finite difference method, and finite element method. And FEA is basically using FEM for that one. And then FVM is more like what most CFD software use. FVM is more like your basic heat transfer cost technique, which you would use basically like node to node calculation. Another kind of approach would be actually not break it down at all. Just consider a big kind of like function of field. Don't worry, we won't go over this because it's like so specialized, and this is just to let you know. And last thing is, this is a really important mindset, is all models are wrong. CFD solution will never be correct in a sense because you're just making a bunch of assumption too. For example, you may have like, oh, you may have a flow, but sometimes you may assume like no turbulence. So there's already like a model that you apply to your problem. So this is very important because this is basically the mindset of whole CFD, is trying to get a good enough solution with good enough required time. So what would a CFD analysis look like? This is basically a table of contents of this presentation. Everything would be structured this way, and we'll come back with a case study. So first thing, very important, define your problem. Is basically like defining requirements. And then you do some research on how others do it, proper techniques, or like what method would be the best for your problem. And then you will basically choose a solver. There's so many software that you can use. Which one would you choose? And then after choosing a solver, you do your setup. Setup is more like punching numbers into a thing, but it involves a lot of theory. And next thing is define your boundary conditions. Every aerodynamics problem would have some kind of boundary conditions in your control volume. Next thing that you would do is create your geometry that influence a lot of things. And then you would do meshing. Meshing is actually the most complicated part. For now, I only complete up to this section, which is already like 26 slides out of like 100 slides now. So you can see how complicated that problem would be. And then of course, run your CFD. And then you also need to look into your solution. Like, how do I know that is a solution? How do I know that is good enough? And then last thing is validation, because never trust your own result before doing any validation. Even like simple hand calculation will show you like a ballpark range. So the workflow is like really simplified. And then we'll go through again each one in pretty deep. And remember, even that process is iterative. You need to revisit certain steps to complete a CFD. So let's dive into the first one, problem definition. Basically, what are you trying to know? So before doing a CFD, take a step back, ask yourself this question, like, what do I want to get out of the analysis? Because of course you need to know your goals. What are you actually looking for? And then what kind of aerodynamics problem am I looking at? I'm looking at supersonic flow, subsonic flow. Is it compressible? Is it external flow? Would it be mixing? Would there be any like combustion? That's something that you need to identify. And what kind of accuracy do you need? Because it determines like how much effort you need to put in. You may put in like 100 hours to get 0.1% accuracy, but a 2% accurate CFD could only take like 5 hours. So that's something that you need to determine, kind of like what detail I want to capture, how accurate does that need to be. And is this a problem that is CFDable? Some problems are not. Just because it's so complicated, any problem is, like CFDable with enough dedication, but it may take you like 10 years to get a PhD to solve that problem when you're doing other stuff. And do you actually need to do a CFD? Because one thing like aerodynamics analysis is about empirical test data. One of the best example I would have is OpenRocket, RAS Aero, the software we use for the rockets. We never do a CFD with those software to get our aerodynamics coefficient, but it's still accurate enough because the rocket did not explode this year, did not explode like a few years in. So sometimes you just don't need a CFD, and maybe like even like hand cal is good enough. Again, this is basically defining your problem and requirements. So problem type. So this is very different because instead of a bulk analysis, you're interested in overall picture, a high level. One of the best example is like a body lift of the rocket. But if you look into local problem, which is maybe like you want to see if flow trap in certain areas, which is sometimes really popular in FSAE because you want to see like if your flow separates. So that's one of the problem type. Flow type, are you doing an internal or external analysis? Like a pipe is internal flow because your flow do not exceed, outside your walls. And then a rocket is basically external flow because it's flying in a large domain. The regime is very important. Aerodynamics, fluid dynamics is the most finicky subject in mechanical engineering because it's just so hard to predict and model everything. And sometimes you need to match certain dimensionless parameters like Reynolds number, Nusselt number, and Mach number. That's just some examples. And how would your flow behave? Is this compressible? Is it non-compressible? That's a very distinct difference between supersonic, subsonic, and non-compressible and compressible because it just depends your condition. It's very different. And what kind of physics effect do I need to kind of consider? Like heat transfer, is that something that you need to know? Is that something that would drive the accuracy of your CFD? Do you need to model any combustion stuff? Is it a mixture or like multi-phase flow? So that's very different. Make sure you know what kind of problem you are going into. Reference value. This is another topic in fluid dynamics. Basically, you need to use some sort of reference to calculate every single thing in your system. Of course, the best example would be area. Like on a wing, you would do basically just the wing shape. And then on a rocket, usually you do your cross-sectional diameter of your fuselage, which is we call it one caliper length, and that is our reference area. Length, another thing, length definition is very important because, for example, aerofoil, sometimes you may use different kind of length to do your analysis, so make sure you use the right one. Pressures, temperatures. So this is two example. One on the right is coefficient of pressure. So that's a measure of a coefficient to indicate if a area have higher pressure than your free stream domain. And then that one is just a corrective flow in a compressor. So make sure you know what kind of reference value you need. And your software actually use this value to compute a result, which you may do the wrong thing. Because if you punch in an area that is like a 1 inches grid, or like, for example, like some funky units, you get entirely different. So make sure you know, do I need to? So make sure you know you use the right one, and just keep record of everything. Yeah, and then sometimes you may like, oh, I will just do half the domain, and then you use the full wing area. Now, basically, you have the wrong coefficient because it's like half the performance. But you're wondering like, oh, why is so off? It's just a simple mistake. So make sure you use the right one. Know your reference value really well. How do you calculate those things? How your software calculate those things? Because each software have different approach. So that's really software dependent. And then the next thing that you would do is make assumptions because aerodynamic problem, you would never factor in every single thing. At least for what we are doing, it's just too complicated and time consuming. So you want to simplify it enough to a manageable level. And then basically you want to compare the result equally. So make sure you use the same assumptions if you have two test cases. Some typical assumptions would be steady state, no transient state, your flow is like steadily flowing. No heat transfer, of course, that's the biggest thing. because you don't want to really do it, or you may estimate a heat flux. That's just something. And then you will do like non-rotating body, which we'll cover at the end. How your fluid behave, you will model it with different models. And again, we'll cover it. And geometry wise, sometimes you would make assumptions just to make your problem easier. The best one, of course, or like the most used one would be symmetrical or periodical. Basically, you have a geometry that is symmetrical, and you don't need to do your calculation twice because they're the same. Surface roughness, sometimes you don't know the surface roughness. For example, Andrew 1, how do we even guess a surface roughness? You don't, you just guess one. Good enough. Sometimes you would do sensitivity analysis to see like if certain assumptions is important. If they're important, you would basically just revisit it or read more about the actual theory. So we jump into how do I know others do it? This part is really important. It's worth the time to spend upfront to make sure you understand the problem fully before proceeding any kind of analysis. Yeah, basically just for you to have a good idea like what you're doing and what problem you're getting into. And to be honest, the problem you're trying to solve is most likely solved by someone else. So you don't need to reinvent the wheel, because just use what they learn and then modify some of the case. Again, to say you know CFD fully, you need PhD plus industry experience or like a lifetime of experience, which I doubt anyone here would want that path. But if you're that, passionate, that would be great because there's not too much CFD specialists, because it's just such a difficult topic. And of course, you want to learn about some special considerations and typical assumptions that you may miss, that you may not think of. And last thing is to validate your setup because sometimes they will provide some kind of results that you can use. And that will be excellent because you can just see if you set it up properly. You 100% will find a different case from your research, but make sure you make your decision based on how similar that is, how similar the problem is, and it will give you a within ballpark, which is good enough as a starting point. So common resources, of course, our best friend academic research papers. Try to use published peer-reviewed papers, but oftentimes they are like really hard to find. So make sure you read through all the papers quickly, understand what they're doing. And usually you will find really bad quality papers. Sometimes you're like, oh, AIAA, they're like recracked. But when you look at it, you may find like that actually doesn't make sense to me, or like you notice something is wrong. So be careful of the reference you're using. Technical publication is probably the best ones because they usually come in the form of a specific analysis with test data. For example, this is a paper that I referenced for my CFD setup. It gives you all the wind tunnel testing data, all the parameters you need to set it up a problem, and even like guide you through how to calculate certain things like boundary layers. Last thing again, software guides. We do have ANSYS Learning Hub, which is awesome. And then it's really software dependent. So make sure you read the right software guide and the right version because they change basically over the years. And you 100% will find conflicted information. You will find three sources talking about the same problem, but they have three different approach, and they always claim, that's the best. So make sure you know the assumption they made, and then just do more research and understand the problem better. Any questions so far? Okay. Now we do how to pick a software. Basically, you need to pick the right tool to use to solve your problem. Software comes in so many different types, and different companies have so many different software. For example, ANSYS have 12 CFD package. Of course, the most well-used would be ANSYS Fluent and ANSYS CFX. These two are the best. It's been around for a while and very for generic, more general problem analysis. Um, Next popular choice would be OpenFOAM. It's an open source CFD software. Most of the people out there would say like, oh, it's a replacement of ANSYS because it's free. You don't need to pay a license. However, setup is way more difficult. And you may want to mess with like command prompt, which is hard because you cannot really visualize what you're doing. But it got its benefit. But ANSYS is probably the best to start with. SolidWorks have their own CFD software too. And it actually is decent for certain case. It's good for starting out, get like a quick and dirty thing that you don't want to do a full ANSYS setup. Another popular choice, Star CCM Plus. I think this is from Siemens, and then I think FSAE is using this one. This is really popular in the FSAE community. I think it's more suitable for like subsonic stuff, but I'm not too sure about it. And this is just another software package that you will find. CFD package even come with something like a GitHub open source CFD Python library that you can use. So basically, there's so much option in the market. Just pick one that is like best suited for you. And most likely they do the same thing. For now, if you know CFD so well, you will know which one to pick, particularly. But to be honest, just pick one, stick with it, and then just proceed. They have different strengths, of course, and make sure like the software is suitable for the problem. For example, for multi-phase flow, like nitrous oxide, ANSYS Fluent is actually really bad for those type of analysis, and CFX is actually way better just because the approach is different. So make sure you use the right one for your software and ask around. So how about you VR's experience? Like some question is like, why do we choose ANSYS? So ANSYS is a kind of like package of software. This term is CAE, Computer Aid Engineering Software. For example, like CAD is just one of the two, and ANSYS have basically everything. Like up to FEA, CFD, even like acoustic stuff, and then you even got like electro stuff. So you got like a lot of things. It's widely used. You probably will find it on job description, either like ANSYS or OpenFOAM Experience. And it's just good support between import and export because we use SolidWorks and they do have a package just directly import a SolidWorks geometry. So that's excellent for a really efficient workflow. So you may ask, why don't we just use SolidWorks? Or why do we use SolidWorks for certain case? It's really good for quick and dirty simulation when you don't want to, like do a whole 2 hours CFD analysis. Maybe you just don't care as much. Maybe you just want to look like how that thing would behave. However, you have nearly no control on the import setting. In fact, the only setting that you would use is just how you set up your boundary conditions, mesh size. That's basically it. You don't have other controls. They also don't publish what method or theory they use. So you actually don't know how much you should trust that result. So that's really good for like quick and dirty stuff because you don't really want to spend too much time for like a simple CFD in the beginning. Of course, as kind of time proceed and more development, you want more detailed kind of like analysis. So we start to jump into the actual CFD portion, kind of the workflow, like really start to think about what the theory. And basically solver setup is picking a right approach to solve your problem. So what do setting up a solver means? You're basically picking certain models to solve your own problem. And then we talk about the followings, basically what kind of fluid dynamics models are out there, what kind of fluid physics model or fluid models we have. Physics model like turbulence model, maybe combustion, but we just focus on turbulence because that's the most general thing that you need. And then how do you solve a problem? So that's very different. And lastly, we talk about how to initialize a problem. It's basically all done in the software. So you need to keep track everything. And of course, it's really difficult to dive into deep because each topic here worth a textbook. So yeah, so we just go for like the basics. We're here to try to get you up to speed what CFD involved and what kind of things that you look for, because what I present here is seldomly grouped together and presented and in this level. So yeah, so we just talk about basics and then again, just read more or do more research. So fluid dynamics model, this is basically the fundamentals of how fluid works. Of course, same as any other problem in kind of mechanical engineering, we start with basic fundamentals equations, conservation of mass, of course, momentum, linear and angular conservation, and of course, this is basically the Navier-Stokes equation. And of course, we solve energy at the end. So after knowing how your fluid behave or move in a space, we look at the fluid itself. We need to define how the fluid behave. For example, like water, do you want it to be viscous or do you want it to be like, oh, infiscous? It's just like no viscosity. So that's something that is pretty common. For example, like ideal gas, is it behaving like a real gas? Would there be any specific models that is better suited for that regime? And then also certain problem would restrict your selection. For example, you can only use ideal gas for compressible flow in ANSYS fluid. Of course, there's more setting that you can play with, but just keep in mind there's limitations. Refer to your research. That is the biggest thing here. So physics model, this is really interesting because you're trying to describe something that is basically impossible to describe. Specifically the turbulence model. Turbulence is so difficult that it worth like someone's 10 years, 20 years of research to understand. We'll go over some typical models used in a CFD software. And this is actually the most overwhelming because it's just so difficult. Like, how do you know which one to pick? So when it comes to CFD, we actually have three levels of models. One is you don't have a model, you directly solve your system. DNS, which is direct numerical simulation, you compute all the flow directly using your boundary condition, using equations. So as you can imagine, it's actually really, really computational expensive because you're solving everything. It's not just like, oh, just like mean velocity. No, you're solving every single thing, which is the most accurate. However, maybe you don't need that accuracy. And then one level down would be try to fit a model to simplify the problem. We come to like start to consider eddy currents. Eddy currents is just basically, your flow come here and then you have some eddy. Maybe something have a bump that caused this. And then of course you have small eddies. Small eddies just like so tiny that you cannot really capture it fully. So DNS can capture everything, even this. However, LES large eddy simulation, we basically only solve for the big one. We kind of like approximate and guess the small ones. And usually you would use this when you want a more detailed flow in your turbulence. Maybe you want to capture some vortex that generated that you want to maybe use or just eliminate. And the final one is the most used. And we'll focus on this one because it's really important. Is RANS. So this is Reynolds average Navier-Stokes. As the name suggests, it's actually taking average of your flow field. So you actually won't see any eddies because it's just taking a mean velocity profile. It's actually pretty accurate relative to the DNS and LES and very suitable for most of the analysis. When you specifically anything that you want to, you only want like a big picture. So how does the simulation outcome look like based on these models? So this is a really good example. I think this is a flame modeling a flame or like a flow just flowing up. And you can see here, RANS is like a mean profile. You get like the general picture, which may be good enough. And then LES give you like some turbulent, but only the big ones. And DNS give you basically everything. Looks more realistic in real life. So this is very distinct difference. And in terms of the actual velocity profile, this is a good picture to kind of like summarize everything. RANS is just taking average. You don't really care like the small details. And LES is basically trying to fit the curve in the actual solution. And DNS is everything. You want like noise, everything. And it's just more difficult at the end. So to kind of like account for not capturing any turbulence, RANs actually have specific turbulence model to use in a CFD. They to capture the turbulence, kind of model it as a velocity profile. Two fundamentals model would be K epsilon and K omega. You will see them very often in research paper that use RANs. They have other models, like I think that one of the models are called something realized K epsilon. So that's different modification based on the fluid type. One of the biggest model that I use personally is SST, shear stress transport. This is really well used in supersonic analysis. So what is the models? They basically use wall functions to kind of describe how close the flow is close to your wall and fit a certain model to that. And then for far field, for anything that is like far from the actual object, we try to use K epsilon, and anything that is close or in the boundary layer, it would use K omega. So to know if you're doing it right or like setting it right, we look at something called wall function. So wall function, y plus is just one wall function. There's another wall function called y star. It's just so many different wall functions. So just make sure you know which one you're using. However, y plus is the most used. It's really important because it allows you to fit your boundary layer kind of flow into a certain model. And this graph is a good graph to describe the requirements. There's some certain threshold on a model. So this is the model itself. This is how the actual flow will behave. So you can see for this range, you need a certain value of y plus to use this model. And you need certain value to use another linear model. Of course, you want to avoid this range because you can see there's no model that really describes this region. So this is really driving how you do your meshing, how you solve it. And we'll also cover like how to do an educated guess at the end. So for like the graph shows y plus more than 5 is good for near wall capturing, and anything between like 330 and 300 is like linear scaling that you can fit onto that equation. So oftentimes you cannot really hit those target, but as long as you're like cautious this exists, you will know like what steps to take. And again, Fluid Mechanics 101 have a good video about this if you want to learn more. And we'll talk a lot more in meshing section. Another thing is about the solver itself, like what is the approach of the solver? So two mainstream is pressure-based and density-based. Pressure-based, suitable for incompressible and certain compressible flows. As you can see, it's more like a one-way process. You don't really need any iteration. You're solving equations by just solve a state, and then state will populate everything else. So it's actually less computational expensive because it's just less steps to do. And for density-based solver, is for compressible flow that the density change so drastically, your probabilities start to change a lot. For example, like supersonic flow, we will use density-based because it's that complicated. And you see that it's actually solving all the partial differential equation at the same time, the 5 equations. So you can imagine it's really, really difficult. And it's just more steps because each iteration, you need to guess your iteration of those equations. So you end up with like another layer of guess. So make sure you use the right one because the software would not know what you're trying to do. It only do what you tell it to do. So if you choose pressure based on a supersonic flow, it will run 100%. But will your result be correct? 100% no, because it's just not good enough. And then another thing about a solver is explicit and implicit solving. Basically, we refer to time matching, how we populate every single cell. Usually, you need to make your cell small enough to kind of like capture certain flow. Again, it depends on what kind of flow regime you're looking at. Supersonic flow may want like more detailed setup. You may need to refine your mesh more. For explicit approach, basically it's just an equation that use the previous state to populate next state. So this again easier because it's just one in, one out. You don't need to solve anything. However, when we come to implicit, you can see it's actually you need to guess your solution. And it's again more difficult because each step you're referring back to yourself and you need to solve everything at the same time. And one kind of approach to quantify if you're doing this right is using another kind of like metric called current number. We will not cover it, but basically that something exists to let you know if you do right or not. Again, make sure you use the right one. Initialization. So when the CFD solver start calculating, it actually guess a solution first. And then as iteration go, it will keep refining your guess and approach a certain solution. So basically, yeah, define how the initial guess is. That's different approach again. It would change the starting point of the solving process. And a better guess, better initialization means you don't need as much iterations because it's already close to what the actual thing look like. And again, faster to save time. And your solution actually converge way faster. Because if your guess is really far away, you may start to accumulate a lot of errors and your solution will kind of break. And you're just trying to solve something that cannot be solved at the end. So make sure use a good initialization according to your own problem. ANSYS free approach, standard, hybrid, and FMG. And in terms of how they look like. So we start with a mesh. Don't care what a mesh is, basically a fluid domain. And then this is the actual result, final kind of like analysis result. And then for standard, it just guess a constant velocity in the field. Is it right? Of course, no, but this is just a first guess. And we come to another one, hybrid initialization. You can see it start to guess differently. You can see it guess like, oh, at the top of that, ball, you have high velocity. So it's doing a different approach. And then the last one, you can see it's actually pretty close to the actual result. And this actually changed so much. During my CFD for Angel 1, I attempt to use just, use the first two ones. I never get a result. But after using MFG, the solution just converged way faster and actually give me a result. So make sure it's the right one. FMG is usually more time consuming because it's actually trying to solve your problem already. However, it gives you the best initialization and long term it saves time and make you less frustrated. So before proceeding, there's a few concepts that is really important. When we say more computational expensive, doesn't mean it's bad. It just means it's more computational expensive. It doesn't mean anything in terms of like quality or approach. Because if you need it, you need it. We only go over like the things to look for. And every setup is very different. Maybe you're doing another regime like hypersonic. Everything may be different. Maybe you're different using different software. And in fact, like if you get into really high standard CFD, one video about SpaceX capsule is they actually do their own CFD code. So if you get to that level, you need really specialized knowledge. And yes, it's like really overwhelming. I don't know what everything means here at first. You probably don't know what I mean here at first, but that's okay. It's just introducing the concept. And the only way to really learn is just to do a CFD. And then ask yourself like, why am I choosing this setup? Any questions so far? No. Okay, I'll get some water first. Oh. Um, Okay. Okay, so the next thing that we talk about is boundary conditions. So this section is a bit different because it's more kind of like theoretical introduction to what a boundary condition look like. Um, this step influences so much how you create your fluid domains. Different geometry have different, appropriate choice of boundary conditions. It also influences how you model your actual domain. We go over like the most common types. Again, there's like so many different boundary conditions you can apply. But to give you like the most accurate information, we refer the textbook that I just kind of like introduced at the start, because I don't want to really mess it up as much. So in terms of must have in a fluid domain. When we say fluid domain, what do we mean? Fluid domain is basically just a geometry, 2D or 3D. For example, if you want your domain look like a jet, 100%, that's totally okay. Even if you want your domain look like a mullet, 100%, that's okay. That's totally fine. But you need at least your inlet, which define where the mass go into your domain, a wall where the fluid not supposed to go, and outlet where the fluid would exist. Of course, for external flow, you have other different conditions, but we'll cover it. But this is basically the must-haves of a fluid domain. So inlet, the definition is where the mass go into the fluid domain. That's different types of power inlet condition that you can set. One is pressure inlet. When you know the pressure of a surface, for a pressure-driven analysis, you don't know mass flow rate or maybe velocity. Maybe that's the two things that you want to know. For example, you will have like a infinitely big source. The best example would be like, oh, maybe you have a pool, and then you want to look at like, oh, how would the flow go out? But you don't want to do this whole thing because it's just too complicated. So you look at this duct, and then just like, oh, it's basically whatever hydraulic pressure here we have, and this will be my pressure inlet. So that is the meaning of pressure inlet. Velocity inlet is when of course, a velocity or a velocity profile. Remember, when we say fluid velocity, a lot of times we're just mentioning average velocity because actual velocity of a flow, let's say in a pipe, will look like this, a fully developed flow. So when we say mean velocity, we're actually just taking average, but velocity actually is different on any surface. So maybe a velocity profile for some reason because empirical research. Yeah, so you can define that profile on that surface, and then you would know the speed of the fluid, of course. For example, you just know the speed. Maybe that's a design requirement that you need. And then you just model it there, and then you will find your required pressure and velocity. And mass inlet, a mass flow rate. This is actually really difficult because most of the time, you don't really know. It's just a model or like a performance requirement that you set. You need to know the mass flow, which is like already difficult. One of the best example is a bleed flow in a gas turbine engine. Because in your design process, you would define that mass flow, and then you would use that mass flow to kind of like see how the geometry behaves. And let's talk about outlet. Again, definition is where the mass exceed the fluid domain. Mostly is just pressure and velocity. Outlet, of course, there's more, but this is the most two commons. Sometimes you can actually set an extra condition called no reverse flow. However, it actually can cause some instability and actually mess up your solution. And when we say no reverse flow, it's just literally no reverse flow. All the flow will exit the domain together. So you won't capture like, oh, like turbulence. You're just saying like, oh, everything goes. So in certain case, it may not be the most accurate condition just because you may want to see this. No. Okay. Okay, so wall. What is a wall? So wall is basically just a physical domain. A physical wall that, of course, like this is a wall, like no mass can go through. Okay, if it was fast enough and enough energy, it could go through. But typically a wall, we don't consider any mass going through. Some good kind of like introduction is in no slip condition. For example, stationary wall, of course, like table. If you want to look at a flow through a table will not be moving. The fluid has zero velocity at the surface, and this is a really good example what we mean no velocity. So you can see the flow is going that way, and then the probe kind of like inject some ink, and you can see like, oh, it actually stays there because no slip condition. So that is really typical. And actually most of the aerodynamics or fluid dynamic analysis would use this assumption. Just because it's really difficult to guess any slipping condition, and a slip flow would look like something like this. But again, it's extremely difficult. So most of the analysis would use no slip condition. How about non-stationary wall? You may ask, what do you mean non-stationary? Like, why would we have that? The best example is just the wall don't have a zero velocity. For example, can anyone guess or give me an example of a non-stationary wall, rocketry related? Exactly. So the rocket, of course, ideal well, everything aligns, perfect tolerance, zero, everything perfect SCAD. And of course, it's not. So this is senior one launch. And you can see after this launch, starts to rotate, right? So this, if you want to kind of account that effect, you would use a certain angular velocity, but most of the time you don't really know that. And maybe that's something that you want to know. Um, and then another best example is a moving tire on a vehicle, or a moving ground. This is actually what most CFD for a FSAE or like even F1. This is FIA. I don't really like FIA, but FIA video. So this is a wind tunnel test of a Formula One car. You can see the tires and the road is like moving. It's actually because if they don't account for those effects, they actually don't get the good result because, of course, like modern Formula One cars like rely so much on ground effect, which is just make your ground close enough to the ground to kind of like use that as your advantage to get more downforce and reduce drag. But if you don't factor it in, they actually find that the whole result will just throw off and your car will not work. So that's some kind of like example of non-stationary walls. Symmetry. So symmetry is really important. It's referring to a fluid domain that is symmetric. Why is that useful? Because you actually cut your domain in half. You're calculating half the math, and your size will be half the size. And what does that mean? You have less cells too at the same time. Of course, it could induce some kind of artifacts, but in general, this is really useful for most analysis. Really careful of what you define for values, because when we slice the domain in half, like this picture, I think it's a concord, and then it's sliced here. So we just slice the aircraft in half, and then this is our domain. So if you use the wrong reference area, you will get the wrong result. And if you're using a mass flow inlet condition, total mass flow, if you define the same mass flow, you get like double, right? Because you're just slicing it in half. However, like remember, like any like density-based stuff like mass flux will be the same because we're just using your area to calculate. Yeah, and then just make sure you use the right area of any reference value because it can throw off your result by half. And you may be like struggling for days, like, oh, what did I do wrong? And then just one single value. Don't ask me why. I know that. So pressure far field. This is pretty interesting, mostly for external flow. So we define a surface as far field if it's far enough across to a certain thing. And theoretically, it is something that won't affect the whole thing. Because imagine if you're running on a track, would the upper atmosphere be affected by you? No, 100% not. Maybe if you're running fast enough, but I doubt anyone can run that fast. So yeah, basic pressure far field is just defining where the location of far, the condition. So this is a really good picture. I think it's a supersonic flow with some kind of jet injection. So you see the supersonic flow comes, And then this is the affected region, and nothing here got affected. Something will look like this, and this is our far field. So this is useful because in supersonic flow, it's finicky to use pressure and velocity inlet sometimes. So this is really good approach. And of course, I will show the approach, and you'll find it's just interesting because the domain looks very differently. So now we covered all the boundary conditions. Now we do create domain geometry. So this is also called pre-processing for CAD software. You do some modification on your actual geometry to make it easier. So what is pre-processing? You set up your control volume. Yes.
Can I ask one question about symmetry before we move on?
Yes.
So like, just thinking of the rocket, if we had a symmetrical rocket, you could chop that in half. But that rocket also has the angle of attack, so it's not like exactly perpendicular. So I'm just wondering, like, do you need to choose a solver that accounts for that, or do you need to account for that with the flow that you're?
So you account for that with assumptions.
Right.
Of course, I think the best example would be, okay, we got our rocket here. Now, like, we got our rocket here. Oh, maybe we have like, oh, launch slugs here. Or maybe like, oh, maybe there's something here for some reason. Maybe like, maybe radio hull, camera, radio hull, whatever. And then fins. Okay, let's just do 4 fins. No, 4 fins. And of course, like, got like your front fin will look like, pointy nose with 4 fins, and maybe some other features here. So like, okay, so what is symmetry? So now you need to make the call of like, oh, maybe I don't care this as first. Maybe I just want to look at a perfect rocket. Oh, maybe radio host. It's difficult because because now your domain is included inside the rocket. So it's so difficult that you oftentimes just like ignore because it won't contribute as much. So now we simplify to this. So you may ask, how do I do a symmetric condition? Let's say, of course, it needs to be symmetry at first. One possible option is like this. But maybe your rocket is actually not rotate properly. But who really cares at this point, right? So you didn't make an assumption of where it is symmetrical. For rocket, usually you use this one because it's more obvious. You capture 2 fins, and this benefit is you capture your flow would be kind of like aligned to your reference frame. Because you're usually a rocket reference frame is aligning with the actual fin, right? Or like one of the fins. So you want to capture at least one full fin. But basically symmetry is just about making sure you're using the right geometry, because even like the rockets rotate tiny bit and your angle of attack could be like this way. Of course, if the angle of attack aligns like, something like this, it's no longer really symmetrical. So so you just make assumptions, because even for an aircraft, right? You can bank, you can yaw, even for a vehicle. So you need to make your assumptions. Usually you interest in, just strict flow because, of course, nominal operating condition. But sometimes you do need a full size. So that's a distinct difference. But that's a good question. Yes.
For the far field, how do you know where to set up the far field before you've run the simulation and know where the far field needs to be?
Yes, that's a good question, which we'll cover in meshing, because you don't really know until you run the CFD. There's some rule of thumb that you can follow, but usually you do a CFD, look at if the flow would be affected. Actually, I have one slide that covers exactly this topic. But short answer is you don't know. And it's a guess at the end. You will see me like talking about you actually don't know, or like I don't know, we don't know a lot of times. But that's okay. That's CFD. That's basically CFD. Okay, domain geometry. This is where CAD come into place after you do all the crazy math. Pre-processing, set up control volume, define how that is shaped, define, if that's solid in your domain. Sometimes you will modify geometry for certain things, for like, like better conversions, just make it less complicated. And you also want to set yourself up for a really efficient workflow because each CFD solving graph sequence is so time consuming. The fact that we can talk about like, 80 minutes, no, 70 minutes now is already like show how complicated a CFD could be. So the key point here is to be efficient and don't make as much mistake. So common task is, of course, you choose a shape and dimension, which is what we mentioned. And then you want to determine like some kind of simplification or any modification. And the last step that you will do is applying your boundary conditions. The size matters for a domain. It's very distinct between a far field, mid field, or near field simulation. It refers to the type of detail that you're trying to capture. And different analysis require different domain size. This is a kind of good example of what is, near, mid, far field. So this is a study, I think is for Concord, just from the nose, I think. No, that looks like XQ. Yeah, that's probably X59. Yeah, I forgot the exact name. But anyways, this study is really it's always done for a supersonic transport aircraft because of course shockwave, the loudness of shockwave is a big concern for supersonic commercial flights. So usually they would do an analysis to look at like, oh, how for like the flight ceiling that they're flying, how loud the ground would have. So this is a good kind of like summarization, I guess, summary to show you what is different field. But again, this is like different. And usually you want to capture as big as possible because your software may interpret like wrongly for certain things. Because if your far field is put near field, it's no longer a far field. So you're applying a wrong boundary condition. So shape is different and they have their own strength. Best example is aerofoil CFD domains. They come with different kind of like shapes, geometry that is well studied. And yeah, someone just determined like, oh, this is actually the best one to use for the type of domain. In terms of like efficient workflow, one thing to mention about a domain geometry is when you see something like this, it's actually pretty good because you can change your angle of attack, your flow without remeshing, which saves you so many times because every time you change the geometry, the remesh, you get different errors, and your mesh will no longer be the same mesh. So you are not really comparing apples to apples. Another approach that you can do for this type of kind of like multi-angle of attack analysis is to rotate a mesh. You create two domains and then you kind of rotate it according to your angle of attack. We'll not cover this because personally I never really use it. It's just so complicated for me that time. But that exists. That's a option. Okay, so for the size, how do we choose the size? Internal flow will not be a problem. Why? Because it's internal flow. There's no size of your domain. For external flow, you want a domain that is big enough to capture all the flows, but you also want your domain small enough to minimize cells. So it's a fight between two things here. For subsonic flow, usually you need really, really large domains because subsonic flow downstream would affect upstream. That's very important, like flow behavior for subsonic flow. Supersonic flow usually smaller actually, and this is because downstream would not affect anything upstream, just because it's supersonic, and this is how supersonic works. For subsonic domain, you will see something like square. It's just about like the boundary condition they use. And another type that you may see is again like aerofoil. And you can see how big the domain is. It's actually 40 times the chord length of the aerofoil. And I think for that, that one is Concorde 100%. I think they use like 90 times or like 50 times of the aircraft length in one span. So you can see subsonic domain is really, really large because you need that large to capture and prevent any like far field kind of interaction. Rule of thumb is like 10 to 15 of your longest length. That's just a rule of thumb, of course. Again, requires like a really large downstream. Basically, you need a really, really large domain to capture every single thing because it would just affect everything. For supersonic domains, they're really interesting, the shape, because for those who don't really know how supersonic like flow will work, of course, the simplest is like, oh, it's flying supersonic. And of course, we like what? Shock waves. So anything here would not affect upstream. So that's the fact. So when you search supersonic CFD for like, let's say aircraft, you see something like this. You see it's way smaller than the subsonic domain. This is the same paper that I referenced. You can see it's like so small because it's just because you don't really care as much, and because of supersonic flow, upstream and downstream are not really coupled. So you can just, get away with this domain for your inlet. Usually you would do this as pressure far field too, because what is far field? Doesn't affect upstream, right? So that is usually the approach. And again, even a ball shape would work. CFD domains are really weird. You will see weird geometries. And yeah, I think this is for F-16, I think. Yeah, typically smaller upstream or inlet can be very close to your actual geometry, and you have way more freedom on how the domain shape. And it's actually good because you kind of eliminate every cell here that you again decrease the size of your fluid domain and again reduce cells. So you're doing less work again. So this is just for reference. This is something I find interesting when I learn CFD. Hypersonic flow even allows you to put your inlet way closer. But however, hypersonic flow is different because your fluid gets so hot, you need to start model different state of your flow. I think they're trying to do kind of like a plasma here, or like just like really hot gas somewhere here. So you can see like two different distinct mesh. That's just for your reference. Don't quote me on this. I know nothing about hypersonic flow. And I don't know when we'll, look into hypersonic flow CFD. That would be pretty interesting. So how do I know the domain is big enough? Again, you don't until you notice convergence in your result. So CFD is not a one-way process. You need to mesh, run CFD, look at your result. If it's right, okay, you're lucky. Usually it's not right, and then you come back, do it again. So again, just rule of thumb to start. If you want to optimize your workflow, you can try to push it to a smaller domain. You need a few runs to see. So you don't need a fine mesh. We'll talk about refinement for the next section. But maybe sometimes you don't need as accurate mesh to begin with to see if the domain is big enough. And then you can do a mesh conversion test to see if that is big enough, if the mesh do not affect anything. This is really way out of scope because it's another topic already. But this is a good illustration. So you can see kind of like the actual flow. Actual flow, the expected flow would be, like, oh, a big boundary and then nothing affected. And then a good domain would be, of course, capturing everything that is happening, including the far field, because that is not affected. However, if your domain is small enough, too small, you can see you're not capturing everything, and it will induce error because that's a mismatch between your boundary condition and the actual flow. So you will see it's really easy to tell if you have a small enough domain for certain things because you will see at the boundary, you will see weird flow behavior when you expect, like the same color, if that makes sense. So this is one of the video I find on YouTube on like how to use ANSYS. And okay, we don't need this. God, L. So he's trying to simulate a typical flow problem, flow across a cylinder. But you can see he did not really capture everything here. The flow is still leaving. So ideally, of course, you would do a bigger domain, way bigger domain. And at the same time, you may look at this and this thing like, oh, maybe I can make my domain smaller. Maybe, just maybe, because like, oh, the same color. However, if you look closely, you can see upstream slightly change too. So again, this is something that's visual, and I'm sure that's a way to quantify, if this is big enough. But my guess would be you would look at your boundary condition and your flow to see if it's capturing everything. And if you look really close, you can see this kind of downstream condition also affect here. So you can see the domain is not big enough because it should be bigger to avoid this happening. And when I say mismatch, because maybe you define this as a far field, but far fields should be uniform, right? But the flow actually is not uniform here. So that's a mismatch between conditions. So this is not big enough. And then for modification, this is one of the best video I can find illustrating what kind of modification we need. This is subsonic flow, of course, FSAE car. And then there's a few different kind of like consideration that we think about. So the first thing they think about is, do I cut the model in half? Do I feature every single feature? Maybe they want to see a comparison between like, oh, no wing and with a wing to, do a benchmark. Stop this bug. And then some good kind of features to modify is if you import it in ANSYS with SolidWorks, it's probably okay because it's actually solid. However, if you use surface-based kind of like exports, like I guess even like stat file could have something like this because maybe you sometimes miss a service. Maybe you're doing service modeling. So this would make, of course, zero geometry because surface have theoretically surfaces have no thickness. So that's one thing. And then the edge. Sometimes you have so many complicated edge. If you play with SolidWorks, you would know when you try to do a fillet, it could render it wrong. Small face is another thing because small face means your mesh also need to be small. And if your mesh is too big, you actually have bad cells that will cover. And then sometimes you just don't need this extra edge. So you're simplifying the model to get a better quality. And then some modification for certain things would be like, do I care the fillets? Maybe I don't. Maybe like something like zero geometry, like a good example would be for a FSAE car. like when you think about a tire, what do you think about? You think about, perfect circle and then a grind. That is like touching, right? Of course, real life, what would that look like is you have your wheel here, and then your tire somehow deformed, tiny bit, contact patch, and then you do this. But however, this is again another whole topic in solid mechanics, right? Like how the tire deforms. So one general modification that most FSAE, CFD, ISO would do is basically just, put the wheel tiny bit under your wall. And that avoid a zero geometry thickness. If you do SolidWorks enough, you see those, shout at you like, oh, zero thickness, when there's, nothing really touching all things. So that's something to kind of modify because you cannot simulate it and the math will not generate because there's no such thing in real world as zero thickness. I think that's all the so that's basically some of the modification that you would need. And then gripping your walls. This is more like setting up yourself for future exports. Maybe you don't know what you want to do in the future. Maybe you're like, oh, do I do a FSI, fluid structural interaction? Basically using the pressure plot to import in an FEA model and then do the FEA. Maybe you want that. Maybe you want to look at like, oh, maybe temperatures. Maybe you want to look at heat transfer. So grip your walls together for post-processing because you can just like, oh, I want that wall to show, that wall to show. It's just easier. Applying boundary condition. This is actually the easiest part because you just click, put numbers in, and then just apply as you define. However, this is also like error prone because it's just manual typing. So make sure you know what kind of setting your software requires. For example, ANSYS Fluent have ANSYS Fluent set of requirements. CFX have different ones. OpenFOAM have their own thing. So make sure you know what is required and make sure you don't miss any boundary conditions. One of the mistake is really easy to make is you apply the wall as a far field condition, and then you're wondering like, oh, why the whole domain have the same color? Because there's no geometry in that domain that time if you define it that way. So make sure you take notes and make sure you document what you change for your software because ANSYS to do everything here, you need to click at least like 50 buttons. So it's like really hard to keep track. So make sure you take screenshots, compare apple to apple. You may find you're doing something wrong down the road, but at least document it. Meshing. Okay, so we'll stop right after this section because this section is 26 slides, which is like 3 sections in a row. One thing is like, what is meshing? Meshing is fighting for your life. Because like ANSYS Fluent will just shout at you as like, oh, poor quality, not enough thickness, blah 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 blah. So you're basically fighting for your life because it's just so frustrating, the whole process. So this is really important and the most time consuming. Everyone will think like, oh, CFD, I will run the software for like, for ever how long. But actually meshing takes most of your time because you cannot use the best mesh in the beginning to see if you're doing right because it will take you like 2 days to figure it out versus an hour. We go through the followings, like what is actually a mesh. 2D and 3D mesh is different, but we focus on 3D because it's the most used ones, at least for us right now. And typical mesh elements, they will change based on what you want to do. And we focus on ANSYS because we have the software the most. And ANSYS have their own kind of like set of elements too. So that's good to mention here. What would a practical meshing workflow look like? And some advanced meshing convergence check. But that is just an introduction. And I would suggest to try it out. So what is a mesh? You're trying to discretize a complicated surface into edges or like small domains. One of the best examples that I think everyone actually knows already is how do you approximate a ball? Most of you would know this, which is basically just a Minecraft ball, because what you're doing is just making it look close enough to a sphere. That's basically what you're doing. And CFD mesh, any mesh, it's basically just Minecraft. And fun fact, Minecraft actually have a FEA software. Yeah, try to look for it. I forgot what it's called. It's something like Minecraft FEA, but if you look for it, you will see like interesting picture. But don't use it for the rocket, please. So we're again, if you remember what is finite volume method, that's something that is more common for CFD. And you may ask, like, with smaller cells means we're closer to real life. Like, if in Minecraft, you create like infinitely big TNT sphere for some reason, you like it. I don't know why, but if you create that, you were like, oh, from far enough, it looks exactly like a perfect sphere. But smaller cells doesn't mean more accurate. You're fighting with round of error. Of course, as your numbers go really, really, really small, the error will go big. Why? Because your computer have limitation in digits, right? So the smaller you get, the more finicky-ish calculation would be. So you're fighting with that. And then, of course, you deal with your discretization error, which is how close your mesh is actually to the actual surface you're trying to capture. So you're fighting two things at the same time, and there will be a sweet spot. You don't really know that sweet spot, but it's just something that you need to try. Mesh refinement. So mesh refinement is an important concept, especially just refine the mesh good enough. We look at a example here. This is from a I think CFD paper on NASA, yeah, missile. So they start with 5 different mesh size, and this is what they find in terms of computational time. When you say CPU time, no one would say like, oh, how much extra time, because if you use a supercomputer, it will be like so fast. If you use, a laptop, it will not be as fast. So everyone focus on the actual computational time or like resource. And then this is the like aerodynamic graph they find. Top one is normal force, and the second one is coefficient of moments. So like how the rocket will rotate if there's unbalanced force because of, I think, angle of attack or like the fin curve change. But you see, of course, a trend is the finer your mesh is, the more computational time increase. But what that means, you get a more accurate result. Not really, because you see the result actually converge after a while. So if you keep refining it, yes, you will get like so close to the actual thing. However, that doesn't mean, like you're just wasting time at that point, because if you look at it, they actually don't go past the biggest one, I think, or like the more complicated ones. So the key concept here is just enough. And again, your result converge doesn't mean the actual answer is correct. Convergence and accuracy is a very different concept. We talk about further sections in further sections. So a 2D versus 3D mesh. Of course, 2D, 3D, very obvious. 2D's mesh is oftentimes zero thickness. Some of the software would not support a zero thickness 2D mesh. ANSYS Fluent, for example, do not accept a zero thickness. You need to do a kind of unit thickness, and it would know what you're doing. And a 3D mesh, of course, is a free 3D domain, which is like more complicated. and more close to Minecraft, I guess, for like on that topic. So 2D mesh is good for cross-section analysis. Like, of course, when you search 2D mesh, the first thing come up must be an aerofoil because that's perfect kind of like application. It's really controllable because you're controlling with edges. And you can spend like way less time to make a really good mesh. And you can pay attention to really small details just because it's a 2D mesh. It's way easier. And it's of course way less computationally expensive because you're dealing with a 2D problem, but not a 3D problem. And then for 3D mesh, of course, is used for the most complicated bodies. Most of the analysis required 3D mesh. Geometry, requires you need really good CAD modeling to get a good mesh. And that is where you fight for your life because you try to, CAD it right, but CAD it good enough. And then you try to do your mesh, but the mesh is shouting at you. So you may like come back and forth, come back and forth. Sometimes it's really difficult to control the kind of refinement you're trying to do. You see why that would be the case as we go. And sometimes you need to simplify geometries, like sharp edges. Maybe you don't care sharp edges. You just like get rid of it. Maybe you don't care fillet, just get rid of it, just make it easier. And it would also change how stable your solution is. And further down the road, it would change how accurate your solution is if your solution is valid. Again, computational is intensive because 3D, you're doing a 3D problem. Mesh also come with like two types, structured and unstructured. So structured mesh is very obvious. It looks, very uniform, usually like square form. They only use rectangular elements. So it's really good for CFD because finite Fourier method is basically just discrete cells. And this is the perfect kind of like self shape. It's very common in 2D CFD. 3D, you can use it, but you may run into some problem. The next one is unstructured mesh. If you try FEA before, it looks like, this geometry because FEA mostly use this type of mesh that we'll cover. It don't have any really regular elements and of course best for like complicated stuff because you can fit every single thing really good. And on the tangent, like STL file actually just use triangles to describe the geometry. Not exactly the same thing, but you get the idea. One thing to note is you can have both type of elements in a mesh that we cover. So what does a typical meshing workflow look like? One, for a 3D kind of like workflow, we'll focus on 3D. You start with a surface mesh. So you start to define how small each cell would be on your surface. Of course, you make sure like have good quality here because you can always go back faster. And then you start with inflation layer, which you would capture boundary layers. This is really important for boundary layers and when you're using rents. And then you start to define your regions, like is it a fluid domain, is it a solid domain, blah, 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 blah. And define transition if there's any. And then you finally create a Fourier mesh. So this approach is common in ANSYS Fluent and OpenFOAM. And ANSYS Fluent have their own meshing software, but CFX just use the mechanical meshing kind of like software. So again, different for different things. And one thing to note is you can generate a mesh from different software and use on different solver. For example, if you want, you can create mesh in OpenMesh, which is an open form kind of like meshing software for ANSYS Fluent is okay. So that's a very important concept because it's pretty flexible when it comes down to meshing. So in terms of element type, we're basically referring to how it looked like and the geometry. It affects so much on numerical stability that we see an actual case. And some element could be exclusive. For example, one of this mesh is only available in ANSYS. We focus on ANSYS because that's the software that I have the most experience. Again, there's way more different kind of mesh that you can use, meshing software. Keep reading. We click on it when I send the slides. In Fluent, there's 4 element types: hex core, a tetrahedral, polyhex core, and polyhedral. So we'll go over each one of it. But before that, what is a good mesh? So to quantify what is a good mesh, there's different metrics that you can look at. But heavily depends on rule of thumb, to be honest. It's just looking at a guide, like, oh, it recommend this quality. Maybe you read a certain paper like, oh, this quality is the best because of certain things. Different software, different definitions. How ANSYS calculated may differs from OpenFOAM. So make sure like you know how your software define it. And again, quality, the mesh quality affect the stability, convergence, and accuracy. So one of the best one to look at is aspect ratio. You don't want your cell to be too crazy, you know. Like on the bottom right, of course, you have problems, right? Because for a FVM method, you want something that is, you know, roughly look more regular. So that's something, rule of thumb is like between 0.2 and 5. And kind of like look at how orthogonal that is. Usually you want something that is less than 70 degrees. However, it is really difficult to achieve in certain case. And that's why I say this is fighting for your life, because you're just trying to deal with everything together. So in terms of the element types, so what does hex core look like? It's the most CFD mesh because they're basically just all squares, you know, all cubes, mostly cubes, more like rectangulars. It would be pretty problematic if you just use this type because you cannot really fit any, you know, good curved surface. You're like basically using a Minecraft mesh, which of course is not the best because you can never capture a true curvature. So this is what a hex core look like. It forms smaller cubes, you know, or rectangulars close to the actual wall. And then the further away from the actual wall, it would just create larger domains because you have less things to capture. So that's very distinct, but you can imagine some of the cells would kind of go over here, kind of interfere. Actually, that's a good kind of indication. Here you can see like this, you know, like chunks, which is not really good most of the time because you're not recapturing accurately. Next type is the most common type in FEA, tetrahedral. Very flexible meshing, again, adapt to any complicated geometry. However, because of the nature of the shape, the normal factors are so like far apart from each other. It sometimes affect like accuracy and stability. And in the same space, you actually need more cells to fit in the same kind of space, such as hex core. Because if you can imagine a cube, you know, and then you break it down into triangles, you have more elements already. Typical shape, you probably get, you know, used to this kind of presentation or graphic of a mesh. This is one of the Taco Link FEA over Senior 2, and you can see this is the exact mesh shape that I use on this analysis. So polyhedra is like best of kind of both worlds. Another common type in CFD to address the cons of hex core and tetrahedral. Each element have a lot of face. It's actually like look like a cube, you know. It provides really good gradient transition. What that means is because each kind of each element looks like this. You know, it can have more sides. However, you can see for each cell, it actually connects to more neighbor cells. So when you do the simulation, because what the software is doing is, you know, try to guess the gradient. So this is really good for solving gradients because you're just taking more effort. So overall, it's more accurate. more like better suited, not necessarily accurate, but better for if you want a steep gradient analysis like supersonic, overall fewer total cells again because your cells are like chunkier, more cells. But it's actually more complicated too because as you can see, so many phases and geometry is not really regular. So again, it's a trade-off of this. So polyhex core is ANSYS kind of like proprietary. This is basically balancing best of both worlds, hex core, ideal type of CFD cells, and then use polyhedral for like really close wall stuff. We have to try and compare like your results. What would that look like is a mix, basically a mix. You see hex core cells and also polyhedral cells, and you see a boundary layer that we go over later. And this is another example, like farther away from the actual wall, you can see it's hex core, but closer to the wall is polyhedral to resolve all the surfaces. And something like, maybe you want turbulent flow capturing. So we look at a case study I found on LinkedIn, which is kind of interesting. So in this test case, they're doing a FSAE front wing as a geometry using the exact same domain size geometry to create different mesh using different mesh type. They go over exactly what we go over just now for all different mesh, and you can see a direct comparison how that look like for each cell. And yeah, I can look at hex core and polyhex core. You will see the difference visually. So from what they find is actually interesting because they want to see if polyhex core is better. And from the kind of like, like just the analysis and result, you can see, oh, maybe it seems to be close. But when you look at the actual computation time, you can see tetrahedral got so much more. And it's not that accurate too, right? Because you can see polyhedral to polyhexacore actually like really close, but tetrahedral actually pretty far away from the actual flow. So actual result, I guess, more like common. This is also how you depend what kind of mesh you want to use at the end. Yeah, just run it, see compared result, make it, coarser, do not make it as fine or you spend like too much time. But this is a good kind of like approach how to decide. And you can see in terms of cell count, of course, the lowest one would be polyhexacore and polyhedral. And they're really close, which makes sense, right? Because they are like really suitable for large stuff, large domain, but requires smaller cells count. So inflation layer, this is something that you modify. Of course, it's done by the software. However, the main reason that we use inflation layers is to capture boundary flows. Because boundary flows occurs in a really, really small regime that you can't recapture with a large cell. Some typical thickness of boundary layer, we're talking like 2 millimeters up to like 20 millimeters, which is like pretty small compared to your whole domain cell size. So you want a good resolution near the wall to capture that. Common issue to tackle with is just like poor quality because they are so thin, and poor transition. Again, they're like from really small cells to really big cells. So you may have some kind of error there. So this is kind of like what it would look like without and with inflation layers. Inflation layers are like look pretty structured when you take a cut. And then again, different regimes have different boundary layer models. So it would affect how you choose that. So how do we size an inflation layer? So how does like a actual boundary layer works? So on a external flow surface, it flow through, just any flat face or any curvature, any face. It would develop a velocity profile. And then usually we define the 99% as the boundary layer thickness. So that is what boundary layer is happening. So you can see like when it's really close to the wall, the change is so big that if you just like do this, you're not recapturing anything. Or like for the total thickness, if you're not inflated enough, you won't capture any boundary flow at all. So because it requires a lot of cells again. So a good one will look like something like this. Fully capturing, but how do I know, I have enough? You don't until you run a CFD because you just don't know. But you can take a educated guess to, get closer to the actual thing. For example, you can, consult empirical data. This is, I think, laminar and turbulent boundary layer thickness of a supersonic flow on a nose cone, I think, from one of the kind of like reference I read. And then, of course, you have your typical fluid dynamics textbook, kind of like models. So this is a good kind of like approach just to, get you started. And you may ask like, oh, which one should I choose? Just choose the biggest one to start with and then see. That's the only thing that you can really do. So for first layer thickness, we kind of circle back to Y plus. So Y plus is kind of like seeing if you're doing it right, if the first layer is thick enough. But what is the physical meaning? So if we look at one single cell, we take the midpoint, and then the distance from the midpoint to the actual wall you define is we call it YP, just a random name here. And then this equation basically relates from density, your friction velocity, which is given by this equation, which is from your wall shear stress. And then you finally have your viscosity of your flow. So this is similar to, like Reynolds number, because it's a dimensional analysis result to indicate if you're capturing good enough. I don't know too much about how it's derived, but yeah, basically this guy exists and this is how we size it. Again, how do I know it's enough? Again, you don't until you run a CFD. Again, we can take a guess again. For example, we just rearrange the equation, and get it. And you may ask like, oh, how do I get wall shear stress? Just, I don't know, just read and research because different problems have different kind of like correlation of wall shear stress. So just find any source that you can use. So checking Y plus. Y plus is not an input. Y plus is an output. It's something that you use to quantify if it's good enough. So usually you would create a plot of Y plus. For example, this is a plot that I created for Andrew 1 during the CFD. As you can see, some walls actually is pretty bad because you can see like, oh, that's so crazy values. But from what I find, I still get within 3%. Using the test case, I still get within, I think, 3% of the actual wind tunnel test. So sometimes it doesn't matter, but it really depends on the thing that you're interested. Because if we're interested in like the shear stress on the skin for some reason, this is not good enough because it's not capturing anything. Yeah, so what now? Like if you know Y plus is good enough, okay, result would be like trustworthy. But if Y plus is not enough, you just like reduce the first layer thickness first, remesh it, rerun it, and to evaluate again. However, if you like after a few attempts, if you cannot get it, then maybe you're wasting time. So maybe at that time you just call like okay, what do I do now? Again, not enough Y plus doesn't mean inaccurate. It's just about how accurate you want. And then it depends on the output you're interested, and a test case CFD usually have it. Again, refinements. Going back. Okay, refinements. So this refinement is a bit different. We're talking about like specific kind of settings to use. Again, the mindset is to refine only certain sections. You don't want a crazy mesh for your whole domain. It's just like too much effort. for the solver. Usually we will focus on actual geometry. For example, like type of refinement that we talk about is surface mesh refinement, volume mesh refinement, and finally adaptive. So surface mesh refinement, of course, is setting up the surface mesh. Few things to consider is what is the area of interest? Is there something that is like so tiny that you need to resolve? And your inflation layer, first layer, like thickness also drive because it would change your metrics. Maybe you would get a really bad mesh if you use too small or too big. And of course, you want to look at the actual size. Like relative size, this is small enough to approximate. Surface mesh will look something like this. Again, this is Andrew 1, and you can see on this mesh apply different type of refinements. Of course, nose tip because relatively geometry is so small. We need a fine mesh. And then anything body, like maybe you don't need as crazy. So you just apply general mesh. The general mesh doesn't mean big, it just means big enough. And then on leading edge, because again, it's a sharp edge, and from what I find, I need a really fine kind of like edge. So I define like really small elements. I think at one point I'm doing like 0.5 millimeters or like even smaller, which is pretty small for CFD. And again, from this, you will see a set mesh because you see like, oh, I'm missing elements. It's not a smooth surface, but that's okay. Because the big picture may not even matter. But spend the most effort try to make your surface mesh looks pretty decent and proceed. So volume mesh refinement. Again, we define how have the meshing software mesh or like connect every single thing. And then in ANSYS, that's a special type of tool that you can use. In your CAD file, you can create another body because CAD doesn't mean like a single body part. You can do a multi-body part. And in a multi-body part, you can do something like this, which is you define the actual volume that you want to refine. And after refinement, you see like, oh, the body of influence, which is the brown cylinder, have way finer mesh, including the sphere. And anything further away, it doesn't look like, as crazy. So adaptive meshing is not something that you do, it's the software do. Of course, you apply settings, but basically the software will refine the mesh only where it requires. It's actually pretty similar to FEA because how ANSYS do adaptive meshing in FEA is look at high stress or high change area and then do a final refinement. And of course, using the software, I did not have a successful try with it because I think I'm just using a refine mesh in the beginning. So any refinement the software do, we just create like an even crazier mesh. So this is something that you will see in adaptive meshing. You see like all the shock wave, it would refine it really fine because you want to capture those change. It's a drastic change. And anything that is not really, like gradual change, not much change, don't have as much mesh. And this is good because you save mesh, and you save RAM, which we talk about maybe today because it's a fun topic. To close out like this part 1 up. And one thing that you can do to quantify if your mesh converge is using something called GCI, Great Convergence Index. This is a method to have a numerical number to see like, oh, if it's converge. It's developed by, I think, some specialists in fluid dynamics, and this resource have like a good summary of what method looks like. Again, quantify with each relative error between each refinement you apply to see if you're doing, enough. I would highly suggest like anyone take on the CFD task this year or like just want to learn CFD to try do this because at the time I'm doing CFD, I don't really have the chance to try it. It's just a bit time consuming for me to keep going back and forth. But I think this is a really good way because in the industry, this is, I think, at least I think in the industry is kind of like a standard way to check. So yeah, try to do this, try to understand this method, and just letting me know how to use it if you figure it out. Okay, so we complete the whole meshing section. And the meshing actually takes like 20 plus minutes. Again, meshing is hard, fighting for your life. So proceed fast enough. So I have to make the rest of the section, just so much stuff to do. Hardware. Hardware, you may not expect like we talk about hardware for CFD because like, oh, why why hardware? And your gaming setup may actually be a ideal CFD setup that you just don't know. Maybe you're born to be, CFD specialist, setting yourself up. And don't quote me anything on this. Anything like for all the previous knowledge, you can treat it like a really heavy grain of salt, like a really heavy one. But this one, just don't quote me. This is at least what I have done. When I build my own kind of like computer. So in terms of the hardware side, what meshing is doing, of course, create mesh, but it's creating a large file with a bunch of numbers to define all the vertices, all the points, all the stuff. So it uses, of course, CPU to mesh it first, to calculate it, and then we store in your RAM, which you can tell already it could be a bottleneck. For the solving process, your mesh is loaded into the RAM again. And then for each solving iteration, you use CPU, sometimes GPU if the software applies. Actually, GPU will help too because it's good for this kind of problem too. And it's a trend in the industry for like high performance stuff. Post-processing, mostly CPU because it's just computing, graphic, and of course RAM. Hardware makes a huge difference. For example, yeah, Liam is still here, I think. When I do the mesh on Liam's computer, it take like 5 minutes-ish. But when I upgrade to my computer, it take like 2 minutes or like even 1 minute. So your hardware specifications change a lot of things. And yeah, and basically, if your hardware is not good enough, you do the impossible, which is crashing ANSYS. ANSYS is really robust in terms of software because one thing that we don't like about SolidWorks is it always crash and shout at you with that, really good sound, the dun-dun sound. And if your mesh is too big or too fine, it actually use all your RAM. And don't be scared if you see like 100% usage, like this is, yeah, look at the spec of this computer, 96 gigabytes of RAM. But if you try to use a really, really fine mesh, you can actually use all your RAM, which is pretty crazy to me when I got my computer because like no way, no way. And this is what you will see usually, 100% utilization, which is fine, which is good to be honest because it's doing thing. And then there's a good quote from from Tim, I pay the RAM, so of course I will use all the RAMs and CPU, which is fine, which is spend money on. So it's pretty interesting. So make sure when you do your CFD, you know your limitation of your computer. For example, most laptop can do 2D CFD pretty decently because small domain. But anything that is like slightly more complicated, you need like a decent computer to run efficiently. Then grades. Not sure. Probably you have more idea than like what I know in terms of like computer grades. But it's not great. You have consumer grade, beautiful, gaming computers and stuff. And then you start getting into high-end consumer grades, which focus on multi-core processing because what CFD is doing using multiple process in the same time. So the more core you have, that means the more process you can run. That means the more time you save most of the time. And then if you get so serious, you get into server grade. We all know this guy. And then if you're like that crazy, you start getting into clustering, supercomputing, and cloud computing, which is actually the trend of the industry, which is using, server racks, clustered cloud computing, so anyone can run a good CFD without, actual hardware. And the trend is in the industry is also starting using AI, because if you look at one of the software, I forgot which one, I think it's called Convergence. They start to use AI model to kind of like fit the flow, and you can get like real-time CFD. So new trends coming up, and CFD is relatively a new technology in engineering, to be honest. And yes, money is equal to computational speed. Usually, again, if you don't size it properly, maybe your bottleneck is your RAM, blah 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 blah. So if the team ever have the need of using like a really high performance computer and we need it, reach out to the department, because I think we do have a computing cluster here. So worth a try, because I think that would get us so far apart from other teams if we can use it. I know FSAE also use it for their simulation, I think. But for what we're doing, it's like good enough, to be honest. Like decent computer is good enough. Just make sure you know your assumptions and accept like uncertainties. And again, if you don't have money, what you can do is only plan around your simulation. Typical simulation time, a fine mesh can take up to like 2 to 5 hours. If you do something wrong, which I do in the beginning, it could take like whole day to run 1,000 simulations, but not getting the right result. So playing around like your daily activities, try to run overnight, if it's not loud, but maybe you need, because that's the only time that you can run it that long. And maybe like, you start a simulation, you have 2 computers. Start a simulation, when you wake up, and then come back when you're free or something. But make sure like the software do not close, because I have a few, incident with ANSYS Fluent that I want you to punch the screen is the result is fantastic. However, it closed the software because it go to sleep for some reason, and I lose all the progress. So yeah, make sure be efficient, because CFD take way longer than you would expect at the end of the day. Yeah, so I think that's everything for today. So running CFD is basically almost your final step. Running CFD basically just means press a button, also look at if your solution is converging, and maybe tweak some of the settings. Yeah, so running CFD is basically you already have everything defined. You set everything up, and then you're really ready to run the CFD. We'll go over like some of the small details. There's not too much to really mention in this section. But every software is different, but basically they're the same. We'll focus on ANSYS Fluent because that's the software we use, and that's the software I use to learn CFD. So some of the typical settings that you will see is a software launcher. For example, ANSYS have this interface that let you set certain options. So if you remember from last time, we talked about hardware. This is where you really set what to use for your hardware. The first setting here is the number of process. So each CPU core allows you to run 2 parallel processes at the same time. So if you have 16 cores, you will do 32 process. So the more core you have, usually the faster CFD would be. However, sometimes it would be more unstable, depends on hardware. Precision, that's something that we always just use double precision, because the modern technology like already allows you to do that. If you don't know what the variable type in like programming language is, this is kind of referring to that, using double versus float. But usually all the modern computers just run on double precision, because all the hardware can run heavy lifting kind of like process. And the last thing is directory. This is really important. Try to set the shortest path. Some software would have limitation on path length. For example, SolidWorks have an upper limit of 252 characters. After that, it will not run any FEA on SolidWorks. So make sure you know the limitation of your software and just, pick a directory that is the shortest because it will be the fastest when it read the files. So the next thing that you can set is using your graphics card. This is really helpful when you have an actual graphics card. However, be careful because when you use graphics cards, that could be a bottleneck. So if your graphics card are like something like GTX 70, like the old ones, it will probably be a bottleneck. So make sure you know your hardware well. But this is how we set to use a graphics card in ANSYS. It actually allows you to run like really fast, which is really good. And you will need to define which equation is solved by graphics card. And different problem have different best suited options. So make sure again do your research. This is some other settings. This settings is more ANSYS specific. I'm not sure instead of OpenFOAM or other software, but basically each software allows you to fine tune some of the setting and computational approach. So one of the thing that you can set in ANSYS Fluid is something called high-speed numeric. This is good for different flow regime as shown here. So sometimes it works, sometimes it actually makes your solution and CFD worse. So just try it out, just try it out to see if it works. Sometimes it will make it more stable or unstable. So just be really aware what you're doing here and keep track of your change. Otherwise, again, you would debug for a really long time, but not really know you already applied this setting. So that's basically running CFD. It's just, fine tuning. And then basically, yeah, we're ready to run the CFD. So the next thing that we'll talk about is how we validate the CFD solution. One thing to be careful is CFD solution and your final result is kind of a different thing because final result is just your physical interpretation, but CFD solution is just the solution of the CFD. So it's tiny bit different. For here, we're talking about how to know the CFD is as accurate as it can. So one biggest thing that you would look at is something called solution convergence. And remember, CFD is an iterative process. So each calculation will be some kind of error. So basically, you need to know if the solution is balancing out the equations that we showed last time. Like all the transport equation, physics equation, states equation. They will have some kind of error, but it's your mission to define how low. And remember, like convergence of a CFD is equal to like low enough error because you're just defining what kind of error you want. For some case, you may want like 0.1, maybe okay. That's just an example. Maybe something need like really crazy, like down to the power of -6, something like that. But basically, you would define it. So this error is called residues. This is a language in the CFD community. Residues are just how much of the equations are. Usually, each software would use a normalized or scale residue because, as you can imagine, a 0.1 maybe degrees error in a large number may not be too important. However, maybe you're dealing with like really cool, like quick 0.1 can actually result in like 5% change. So that's something that more representative. And again, all software have their own definition, so make sure you know what they means in your specific software. So we focus on RANS residue monitoring. it's very common that, this is ANSYS fluent. There's some terms that you will look at. This graph shows, you can see the x-axis is iteration, and then the vertical axis is scaled and normalized residue. So by this plot, you will monitor how good the software is guessing. Something that you don't want is, like too much spike. For example, you can see some spike in this graph already. That's not too good because it kind of indicates a unstable solution, and you will see an even more unstable one in the case study. So this is the kind of like detailed view of what each column means. And then you have your fluid dynamics and physics equations. And then the last two terms is your turbulence model. If you remember, we're talking about K epsilon, K omega, basically those terms. So you need to kind of like sit there, monitor a few iteration, and then kind of like let it run. So for residues, there's some rule of thumb that we can use. This is the ANSYS default. Basically, it's pretty low, pretty, like error prone. It's okay because you're just starting out. Yeah, usually just if you don't know what to apply for settings, just use what the software gives you, because that's already, like that's a default for some reason. So just use it. Don't mess with it if you don't know what you're doing. Typical largest values are basically what's shown here. Like to the power of -3 for your physics, more like transportation equations, and then for energy you want a bit lower because you need that kind of like resolution to capture a good CFD. And again, you will find a lot of recommendations. For example, someone would suggest for laminar flow, you may want to use even like to the power of -12. For turbulent flow, maybe it's -6 is good enough. So make sure you know what residue you need, because that dictates how many iteration you need to run. Another thing is converged residues doesn't mean a converged solution. This is a distinct difference because it only means the fluid dynamics kind of model converge, but that doesn't mean the thing that you want converge. So you also need to monitor your design parameters. So for example, this is one of the earliest test case for the CFD, and this is a lift plot relative to the same CFD run. And you can see if for example, if we define like, okay, maybe this is convergence, maybe we define this part is already converged, but you can see the lift plot actually does not converge. It's actually still dropping, right? So that's something that you don't really want because that just means what the parameters you're interested is just not accurate enough. So sometimes you want to wait a bit more, but at some point you kind of need to call it because and you will see in the test case because you're just wasting time. Maybe you just need to change some of the settings. And again, convergence doesn't mean accurate result. Converged CFD just mean the solution converge. The software is already as good as it gets. One of the good kind of like another field is like damping. You can see in what we want is usually critically damped. That means it will only get to a certain point and then already converge to the solution. And overdamp is something that sometimes you don't want because that means you have some kind of error to your desired target. CFD solution is exactly this plot. So the residue can converge. Basically the overdamped case. But something that we want is really close to critically damped. So you want the solution to be also converged too. So keep this in mind because it changed basically everything. So next thing that we talk about is how to validate your result. Basically, you need to look at the physical meanings of the numbers. you can get a good number, you can get a good plot, but you never know if the number is correct. So never trust your result any apply to all the analysis that you do, even like FEA, never trust your result before you do any validation. Always assume your result is wrong because usually it's wrong the first try. If you have coding experience, the first try would always be wrong, basically. And by validation, sometimes it's just, looking at a reasonable number and be careful of how you define accurate enough. Because sometimes, maybe the margin of error is too big. But maybe sometimes you define too small. So make sure you know your definition. We'll go over a few approach, mostly just hand counts. That's the easiest one. You don't need to do anything. And just write on a paper or something, that's good enough. Sometimes you reference empirical result, like testing, and then finally physical testing. So hand counts, I think everyone would know what hand calculation is. For example, this is the tackling FEA. Originally, I plan to do a validation with string gauges. However, there's some kind of like routing issue on the PCB. The result is not accurate, and it just gives me something that is like really wrong. So I end up doing a hand calculation, and then just kind of like verify. So hand counts, usually you need to do some kind of assumptions, because if you can hand calculate accurate as the FEA, there's no point of the FEA. If you can do something that is 1D on the paper. So here I assume the bulkhead is just, your typical plate. I ignore all the stress concentration and then just look at one single point. And the difference is like pretty close to what I see in the FEA, right? It's like 20-something% off. So usually hand count is just telling you if your CFD solution is close enough, at least in the same magnitude. Because if it's like 200% off, maybe it's too inaccurate. So the next thing that you would use is empirical results. They're basically derived from empirical models. One of the best example would be nose cone, for us, because you will notice open rocket RAS Aero never run any CFD, but they use empirical models to get all the aerodynamics coefficient. So that's how you would do use the empirical result. Or maybe you're doing some analysis with maybe let's say a pipe. So you consult those kind of literature, and then just see if this is close enough. Again, you will need to do some simplification, because again, if you can calculate empirically, there's no point of you doing a CFD most of the time. So yeah, make sure you know your assumptions again. So the last thing is test results. This is usually not too common for us, as a student team. We cannot really do too fancy actual aerodynamics testing, but this is how you would do in industry. For example, you can see a wind tunnel test. That's a good thing, but wind tunnel test usually is really, really expensive. And another approach would be, something like MotoGP, or even you can see on Formula One. You take actual measurements when your machine or when your design is actually operating, and then you would take those values to compare to CFD result. And then kind of like fine tune your setup. So basically it's just CFD test, most of the time. So you may ask, what's the point of CFD if I'm going to test it anyways? Of course, you want to know some kind of certainty of a setup, because you usually won't start with your actual kind of like geometry, just because sometimes you don't know if your setup is correct. Usually you can look back into previous test data to kind of fine tune what you're seeing. And at the same time, CFD allows you to observe certain things that you cannot really measure or like record. For example, like flow separation, that's something that like harder to observe. In Formula One, of course, you can use like paint to kind of see how the flow is behaving, but that's something that is like more difficult to observe in the real world. And again, like some other examples are turbulence and vortexes. It's just a bit difficult to observe. So CFD allows you to really look at the true flow details without, maybe you're doing a combustion chamber CFD. How will you, put a camera or like measure turbulence? You cannot really do that. So that's CFD give you the insight of the actual flow. And again, it's less expensive than physical testing. You'll be really surprised how expensive physical testing, such as wind tunnels, are. Sometimes actual flight testing is cheaper than wind tunnel tests. It's that expensive. So it's just, it's just easier at the same time because you can't just sit at your computer, without a whole test campaign. And it also allows you to do integration with other analysis like FEA. This is what we call FSI. And you can even do kind of like an interactive FSI, which is you first use your CFD result to determine the formation of your actual object from using FEA, and then use that deformation feedback to the CFD to do another flow simulation until they converge. So that's something that you can do with CFD. Okay, now case study. So case study, this part is the most shaky part of my presentation, just because there's still a lot of things that I don't really understand what go wrong. So disclaimer, again, there's a lot too much thing that I can do better after like so much work have been done. The CFD project is partial success. You'll see why at the end, but it's really close to a complete success. And something that I really regret is I lost some of the documentation because I don't really know what I need to document at that time. So yeah, make sure you do your own documentation because it helps you so much on debugging. Because most of the content I use this slide actually come from my documentations. So make sure you do a good documentation on all the settings, all the graphs. This whole lecture is really based on my experience on the CFD project, and you'll see why when we keep going. And please continue to learn about how to do a rocket CFD. My work is just the starting point of a really high quality CFD. So I'm really looking forward to that. And again, we will blend some of the section because they're so interrelated. It's too difficult to separate. So, but generally, I would use the workflow that we have discussed. So problem definition. Basically, my goal for the CFD project is to really develop a deep understanding of CFD analysis for the team. And I will also want to develop a validated CFD workflow and set up for any future work that we can do. Target accuracy, that's something that I don't really know. So I'm just taking it as accurate as I can. Because that's the really first actual CFD project that we have on the team. So what's the problem? The problem is I want to get different aerodynamics coefficient under different angle of attack of a rocket. Mostly it's just coefficient of lift. That's a big thing. Coefficient of drag, and finally the most important one is center of pressure. CFD allows you to do further analysis than just empirical models. So that's one of the biggest thing that we want because we know supersonic flow is really finicky in most rocket trajectory software. So the approach I kind of determine is just one, the team don't know what we don't know. So let's just use a test case to validate the setup and then apply that setup to the actual rocket. So the next thing I do is literature research. aka basically this whole entire lecture. So the first question that I kind of ask myself is there a common way to set up a supersonic CFD, something like a missile? Because to be honest, for our scale, what we're doing is basically a missile, passive guide missile. So looking something like a missile is better because if you search any like rocket, you only search like massive structure, which is like too much for us. And the level of analysis is different. So after kind of like reading so much resource, I find a reference. Basically, it's the case CFD of the Concorde that I show in previous slides. That is really good because it showcases like all the things that I can't need. And that's, to be honest, that's the only reference that I can find with that high quality. And then next thing that I ask myself is there any good, well-studied missile-like structure that I can reference? And yes, it's the NASA missile. Why? We see why I choose that. It's just because it gives me basically everything. And I also ask myself, what are the things to be careful? So that's something that I don't really know. And then basically the whole lecture content is about what are the things to be careful, Y plus models, assumptions, basically those things. So let's look at this test case. There's two resources that I reference. They're all from NASA technical. I forgot. I think it's technical publication. Basically, there's two wind tunnel tests with almost the same rocket. And why you may ask, why do I use this test case? So first is it's basically the scale of our size, and you will see in the next slide because dimension wise is actually pretty close to what we have. And it's really recreatable because it just gives me every single detail. It also gives me wind tunnel test data with so much different conditions that I cannot really find any paper that gives me. And again, this geometry is actually well studied within the CFD community. So that's why I use it because someone have done it already. I know roughly the ballpark, what we are looking at. So this is cover all the details that I reference. And then because at the time we're using the rocket killer motor. So we are predicting something around above Mach 2. So I just choose this case and then just use this case for all my CFD, setup, learning experience. So the next step, choosing a solver, basically it's just ANSYS Fluent because that's the team software that we have. It's a good package. And then again, it's just good for this kind of analysis because someone have done it. We have experience with CFX, but from what I read and look, Fluent is better suited for this kind of geometry, this kind of problem. So I just stick with Fluent. And of course, we want to add Fluent to the team's kind of like toolbox because it's actually kind of difficult to use. So I just like, okay, may as well just learn Fluent. So we get to more complicated part, like all the models that I use. So setting up the solver, the first thing that I need to define is the fluid model, which is ideal gas. This is because most literature actually just use ideal gas. And ANSYS Fluent actually requires you to use ideal gas model for supersonic flow. I think there's some setting that you can use to change the model, but this is the general restriction with supersonic flow in Fluent. The next thing, turbulent model, RANS. Why? Because that's basically Fluent. Fluent is RANS-based solver. And we don't really need small turbulence because I am interested in the big picture of the aerodynamics coefficient. So yeah, we don't really care too much for small turbulence. I'm pretty sure you can do small turbulence, like using large eddy current, but it would be like way too detailed for what we need. And it's just, it's a scope trip at that point. And again, industry standard use RANs a lot of times because it's just fast, efficient, and good enough accuracy. So for the RANs turbulent model, this is the model I use, K omega SST. I think it stands for shear stress transport. Basically, this model I have seen on so many resources. I read through like 5 to 10 different published CFD results of supersonic flow. They all use this model. So because understanding each model requires so much time because they're a textbook worth, probably like a few textbook worth. So after kind of like struggling with what model to use, I just like, okay, let's just use this and see what happens. I also try to use K epsilon just to see what happens, but to be honest, I get no result, no good result. So I just stick with this model. It's pretty stable at the end. For the Y plus, around this range is like good for those boundary layer resolution. I did not really achieve it for most of the simulation. You will see why when we go down to the slides. It's just a fight between the mesh. So again, solver is density based because supersonic flow requires density based. It's just more complicated because you have so much change of fluid properties across shocks. And we use implicit model because this is actually recommended in the ANSYS Fluent User Guide for supersonic flow. And all the literature also use implicit. So yeah, I just use implicit. Initialization, initially I try to use hybrid because that's an easy setup that you can use. But I find the solution is really unstable. So I use FMG at the end, which is really good because it helps convergence and I am able to hit convergence in most of the case. So next we look at the boundary condition and how I create the domain geometry. From the main reference paper, I determined like, okay, this curve domain is good, parabolic, and I will also apply the same boundary condition because the flow regime problem type is exactly the same. And for the kind of like NASA missile, I want to get something that would yield max fin bending. So I just slice it in half, just 90 degrees from the flow. So it will give me full bending. Okay. So from the main reference, which is the Concord CFD, I determined like, oh, parabolic type domain is the best because that's what they use. And I also use the same boundary condition just because the fluid problem they're trying to solve is exactly what we are trying to do, aka, plotting out the aerodynamic coefficients and center of pressure under different angle of attack. So we just use the same thing here. And then for the NASA missile, it will be symmetry along the fin center plane. I want something that would give me max fin bending, so that's why I use it. So this is what the fluid domain looks like. And you can see the rough size. I think this is the initial mesh, the more earlier mesh. So the final one that you see is slightly different, but you get the idea what kind of, body of influence or what kind of boundary coordination that I use here. So let's get to meshing. This is where I fight my life. There's so many iterations to get a good mesh. So I start with different shape, just to look at like, oh, what would change? But at the end, I still determine parabolic domain is the best because we can also change the angle of attack really easily. And it's just the most stable one among every other domain. So there's some early attempts. I think this is first successful meshing with Liam's computer. And you can see it's just like too fine, I chased for a really, really fine mesh, which is too much for Liam's computer. I think it took like 20 minutes or something, which is a shame because it's just too fine that if meshing takes 10 to 20 minutes, the solving portion probably would take like days. So no, that's not a good mesh. And then this is another early attempts. This is very, ANSYS online tutorial type domain. You should just say rectangular box. And this is also not a good mesh at the end. So this is the final mesh. If you look at the actual references, really similar. And you can see some, I use body of influence refinement around the rocket. The size is kind of like random. So more study will require to make it bigger, but this is what I find like, okay, that's pretty good for what we are doing. This is some of the details, again, add a nose tip, fine, because nose tip is like very sharp in the simulation. Fuselage, just general stuff, because you don't need as much. So I'm just saving some mesh, kind of refinement for other sections. The leading edge and trailing edge on the fins are really, really fine. That I actually run into problem. And then you will see it. For the element types, I use polyhedral because it's so stable for this setup. I try all the mesh type in ANSYS Fluent, but I still find polyhedral the best for this setup. Boundary layer, I refine so many times with a lot of CFD solution because you will see why I say fighting for my life in the next few slides. So the first thing ANSYS Fluent or any software will show at you is warnings and poor meshing. This is one of the poor meshing that I see when I start to do it. This is, I think, from the surface mesh. I actually have really bad element along the fin edge just because the fin edge is modeled as a sharp edge. So it's actually really difficult to refine. Real difficult to refine the leading edge because it will just keep generating stuff. And then you may just ask like, so if you say the mesh is not small enough, we can just make it way smaller, right? Yes, kind of, but that also means your mesh will be really, really small for your boundary layer and just your volume mesh. You end up with like really fine mesh, which is too fine. So it's really a balance. So the CFD result, initially you look at, fancy graph looks, all right, because that's what you would expect from, a 0 degree case, which is, shockwave, really good shockwave formation. And the plot is actually pretty good too, because all the shocks are like pretty, what you would predict to be seen. And then for the Y plus, it's actually also pretty good. I'm able to hit what I want to do. However, that doesn't mean this is a good CFD because I actually have so much problem with convergence of solution. And then this is where the partial success come in. So when we look at a zero angle of attack case, this is what I get for the center of pressure. And this is what we have in the NASA paper. It's actually pretty close. It's like 1.7% off. It's like really like almost right on. And even like up to high angle of attack is still like 3% off on everything. However, if we look at the convergence plot, you can see really bad convergence. You can see this solution is really, really unstable. You should see something really smooth and residue keep going. But you can see I go up to 3,000 iteration and it's still just like struggling to converge. And then if we look at the coefficient of lift plot, it converge. It makes sense, right? Because zero angle of attack, no lift. But if we look at the coefficient of drag, you can see it's actually not converging. So that's something that you would experience when you first run a CFD test case. Another thing that I struggle with is unstable solution. For example, this is some of the earlier failed attempts. You can see it's just really, really bad. It start like pretty good, right? Like the earlier a few iteration, and then everything just kind of like keep going off. And the spikes that you see is actually due to the software just have drastic change in property for certain cells, so that it just like increase the residue so much, so that indicates some of the cells are not, too good. And then this is another really bad example. Originally I thought like, oh, I already get it, and then it start to jump and kind of like diverge, converge, diverge, converge. So that's something that you don't want to see, but you will see in the beginning. Most likely this is due to a mesh problem, especially near like the small cells near walls. That's something that also I observe, but I cannot really deal with it. It's just I don't know what's going on. So what can we conclude from the test case? Again, this is already like really high hours in per week. It's already like roughly 2 months worth of work consistently, 30 to 50 hours per week. And although the macro result, all the coefficients looks pretty decent, but to be honest, I do not have time to know what the actual convergence. So because at that time we are kind of like running out of time for a good CFD. So as per like, basically all the engineering analysis or design that you would do, you need to make a call, to at least conclude if this work is, okay, or like how can we use it. So what I conclude is, okay, the CFD setup is actually going in the right direction because I keep getting better results. And the CFD is as good as it will get at the time. I'll probably need to spend another like a month or two to kind of know what that is. However, that's just so much task, that's time. So the CFD is actually a kind of like a study project, but not a actual project on the critical path. So at the time, we need to like, okay, this is what we have. But again, the setup is still useful because, result wise, we get like something, in the ballpark. But if we want to use that result, we will need to acknowledge that, okay, we need a really large margin of error. Just because, we don't know what is causing it, or we don't know the actual accuracy. So the next thing that we do is a FSI. We did not really run any proper CFD on proper CFD. What I mean is we did not run a aerodynamic analysis for Android 1 with CFD. This is mostly because we need a FSI required for the fins that we have. And that's not something that you can just get from, like estimation, because it's actually pretty difficult to know where the center pressure is. So we do both things. We do a hand count of the fin lift, I think, and we also do a CFD. So just to compare the result. And I basically just use the same setup, from the test case, and just, kind of nudge to myself and the team, we need a really big factor of safety for the FEA result because it's only a partial success. Flight condition, it's very similar to what we use for the NASA test case. That's why I use the NASA test case, because that's basically the same condition that we want to know. Because we want to do a worst case scenario. We do everything at sea level. So that's why Mach 2, even though it's Mach 2, we just adjust to the sea level speed of sound to give us the worst case. Again, I don't know why I kind of missed some of the documentation, like key documentation, like convergence plot, but not my best moment. So make sure you do all your, documentation and take your time to do a CFD. So this is what the domain look like. Is basically the same thing as the NASA test case. This is the mesh, again, really similar, some small adjustments based on the actual rocket, because our rocket is slightly longer and bigger. And this is a close-up on the fins refinement. So result, I actually achieved convergence for Angel 1, which is surprising to me at that time because I was like, oh, I cannot get anything. But for some reason, it do converge. For some reason, I decided not to take a screenshot. I don't understand why I did not take a screenshot after like 3 hours of simulation time. So please make sure you take a bunch of pictures in the future. So this is what the rough plots look like. That's something that it looks really good because visually it's what you would expect to see on this kind of simulation. Like all the pressure distribution and density distribution around the fins, which is exactly what you expect. And then the rocket, overall everything looks all right. Again, this doesn't mean anything. And if we look at wall Y plus, it's not too great. It's only, it's like okay low. It's like rough, at least it's not crazy high. So that's a good thing already. However, I attempt to further refine it, but what I find is the further I refine, the solution, the solver requires more time, and it actually gives me more error. So I decided, okay, we're running out of time. This is what we will, take. So next thing, FEA. I won't go over the FEA result, the setup because that's another topic. But this is what we find. Factor of stage 3, most likely due to stress concentration. So from basically the engine CFD, I conclude, CFD conversion is a good first step for a good rocket CFD because this time we actually run on our actual rocket. So that's a good indication already. More Y plus could be improved. Most likely just, refine this first layer height to achieve that Y plus. But it's good enough for what we need that time. I cannot really, conclude anything, exactly saying like, oh, CFD is trustworthy, or, even though Andrew 1 come back in one piece, the fin damage, but it's because of ground impact. Although that is the case, but that's just after the fact, So I won't say the CFD proof, like to be honest, trustworthy. It's just a good starting point. There's some improvement that I think we can do to make it better. The first one is mesh quality. We really need to see how to make better mesh for close, for near wall, kind of like Y plus, how to achieve proper Y plus. Another thing we need to know is for the model, what do we need to make it better or better suited for a CFD? For example, all the sharp edges, to be honest, they may not be that important. Or maybe there's some kind of threshold that we can use for those sharp edges. So that's something that we really need to know. Documentation workflow. ANSYS actually have a automatic like generation process that would give you a bunch of graphs for each run. So the team should actually look into how to do that properly. Maybe write, some tiny code to automate that process. Make sure we have all the pictures, all the stuff that we need each time, so we can refer like, okay, we're actually improving the CFD, or are we going in the wrong direction? So closing remarks. That's just a few things. Again, thank you for your interest in this big topic and my work. In this presentation, we go over, all the fundamentals of CFD. It's pretty deep dive compared to your typical YouTube tutorials. We introduce a CFD workflow. Hopefully, you know what you need to do for a CFD now. And we also show, look into a test case that we have done. This presentation basically gives you everything that I learned from the project, which is worth like probably 200 hours-ish at that point. So probably more, to be honest. So I hope this is like an excellent point for future development because it will be. I hope this presentation also serve as the documentation because if I try to document it, it would take really, really long. And I can't actually write a book at that time because I actually can. So some of the future development, again, this CFD project is just a partial success. But it's a good start, for our team to learn more advanced CFD. Even a partial success CFD taught me roughly like 150 slides worth of contents. So a full success CFD will give like so much stuff. By the time we will know the exact thing that we need to look into for that simulation, that's something that I think we can look into is what is the actual reason of the poor convergence of NASA test case? Because that geometry is so common that I think the team have the capability to make a good convergence CFD on that. We also need to look into more meshing techniques that will be a better way to improve that mesh. Or maybe you use different element type, maybe you use different settings, like transition. Just make sure the mesh is good. That's something that I really run out of time at that moment because each mesh takes so much effort to know what you're doing. So I hope this is something that the team will look into more. Again, something that I mentioned last time is how to modify the geometry better. The only geometry I modify is like a small radius on the nose cone, but I don't think that is enough to make a stable mesh. And again, automated reporting. So we always have the documentation. And again, please keep working on building a CFD knowledge. Our team actually have a few attempts, but I think this is the first proper CFD study. Reveal what each setting means, reveal the actual fundamentals. And I think we can continue to use the NASA test case because it's already there, and even use the Andrean, case to improve the CFD setup because we have flight data that we can reference now. So thank you so much, and I really hope to see more CFD work from UVic Rocketry. I think it would be awesome if we can do our own, accurate CFD to look into certain stuff that we really want to know, such as dynamic stability. That's something that we really need to know. Maybe even like aeroelasticity. That's something really advanced CFD work that we can do to really optimize something like fin, composite fin. So yeah, I hope this slide gives you a good content and good idea what CFD requires. Again, this CFD slide is basically almost a textbook worth of content. This is just to get you started, and I'm sure with this presentation, you're able to go even further from what I do for my CFD work. So thank you, everyone.